turn to the panel. And this panel is led by someone who is no stranger to anyone focused on carbon-free clean energy innovation. In fact, I interviewed our next guest many times throughout my career as a climate and energy journalist. Josh Freed is the leader of Third Way's Climate and Energy Program. In this role, Josh oversees the strategy to advance policies and change the conversation so that the United States gets to net zero by 2050 as fast and equitably as possible. Josh, thank you for being here. It's nice to see you again.
Great to see you, and thank you so much for being here, and thank you to NEI for asking me to join this very interesting set of conversations. I'm so pleased to be here with Paul and Chris and Melissa, who I will introduce momentarily, and then we'll jump right into a conversation. All of you in the audience, please continue to ask questions for our panel through the question function on the right-hand side of the screen. First, let me introduce Paul Chodak. Paul is the Executive Vice President of Generation at American Electric Power. He is responsible for the management of all electricity generation and generating units for AEP, Ohio Valley Electric Corp, and Indiana Kentucky Electric Corporation. Paul, thanks for joining us.
Good to be here.
Next, we have Chris Levesque. Chris is the President and Chief Executive Officer of Terrapower, which of course is funded by Bill Gates. Chris leads this nuclear innovation company in the pursuit of next generation nuclear energy solutions, and were recently awarded the U.S. Department of Energy's Advanced Reactor Demonstration Project Award. Good afternoon, Chris.
Hello, Josh. Hello, everyone.
And finally, we have Melissa Lott. Melissa is the Director of Research at the Center on Global Energy Policy at Columbia University, and Melissa specializes in technology and policy research, working to increase our understanding of the impacts of our energy systems on air pollution and public health. She directly applies this understanding to help decision makers mobilize technology and policy solutions to support the transition to low carbon energy systems. And Melissa has authored more than 350 scientific articles, columns, op-eds, journal publications, and reports. And we will not be quizzing Melissa or anyone else on all of those publications today. Welcome, Melissa, and thanks for joining us.
Yeah, good to see you, Josh and Paul and Chris. Good to see y'all.
So let's just dive right in. And let me pose an opening question for all of you. What do you see as the future of the electric grid, and how are you or the industry going to meet this challenge? And we can start with Paul.
Well, Josh, I think the need to decarbonize is going to set the tone and really drive much of what we see. We're headed toward a much more complex, much richer grid in the future with much greater customer interface and control. With distributed generation, so no longer is it just central generation, there'll be two-way power transfer between load and source, demand response of grid edge devices, much more automatic interface to manage demand response, layer on top of that EV, storage, and you get a very rich, complicated system, all geared around helping to drive down carbon emissions. And the utilities are going to be in a position where they're going to have to manage that complex environment. They're going to have to be able to orchestrate between those grid edge devices and the bulk electric system, and with central generation, transmission, and distribution, all to follow load on a minute-by-minute basis and deliver safe, reliable power, but most importantly, to do that in a way that actually maximizes the efficiency of the capital invested. You really don't want individual systems operating independently. You want them operating together as a system to minimize the overall cost. And really, carbon policy is going to drive the pace of that change.
Thanks, Paul. Chris, anything to add on that?
First, I'll start by saying, us nuclear developers didn't used to have to think too much about changes on the grid, because nuclear was always sitting at the bottom of the dispatch curve, providing base load power, and Paul and other folks worried about transmission and distribution. But when we look at the next 30 plus years, there's going to be so many changes driven by coal retiring, driven by so much wind and solar capacity coming online, which is an intermittent source. really requires companies like Terrapower to understand the grid more. And that's supported our thinking on developing the Natrium technology, which is not only a clean energy source, but is going to provide thermal storage via a molten salt storage system. So we'll be the first nuclear plant that's sitting at the top of the dispatch curve and participating in entirely new markets. So we've had to get a lot smarter on what we think is going to be happening with the grid. Even our chairman, Bill Gates, if you picked up his book recently, How to Avoid a Climate Disaster, he personally has spent a lot of time trying to understand these things. So certainly we see a big growth of wind and solar, but I think Maria in her speech mentioned the Washington State study that was completed last year that showed, sure, many markets like Washington are going to increase their wind and solar, move towards carbon free. But it was so telling that in that Washington State case study that they said, if we implement nuclear energy as part of that last layer, after we've reached 80%, wind and solar and hydro in their case in Washington, if we implement nuclear in that top layer, we can reduce costs to the ratepayers by $8 billion. So that's $8 billion in a state with 8 million citizens, $1,000 per citizen. So you can just really see the need for nuclear in this changing changing electricity market.
Thanks, Chris. Melissa, let's just turn to you for any comments on the future of the grid and building on what Chris and Paul said about how the industry might meet that challenge.
I mean, at a high level, we know that as we move into the future and we look at decarbonizing the power sector, but more importantly, decarbonizing the economy, we're going to grow the power sector. And within that, we're going to want, if we want to keep the costs low, 3 kind of buckets of technologies that different parts of the industry will invest in different ways. And so the first one is these, low cost variable renewables. So when they're around, they're really cheap, and that's great. They're not around all the time. We know this. We're pretty good at predicting when they'll be there. Every single technology has moments when it surprises us, but for the most part, we know what's going to happen with these technologies. Bucket one, that's a lot of low cost power we can have. But the second bucket is equally as important, which is the firm dispatchable power. And that's where nuclear comes in. That's where other just 24/7, 365, those facilities are available when I need them to put power into the system so we keep the lights on. And the third bucket is energy storage, and not just the batteries that we think about that get us through hours, but these things that get us through weeks, where across seasons, longer term storage. So you can talk about fuels that are produced with electricity, you can talk about hydrogen and others, but the bottom line is what that means for the grid and what that means for investors is that we need to build up the grid quite a bit. And something that's very interesting that's come out of a number of different studies, including the Net Zero America study that Jesse Jenkins and his team put out at Princeton, is that we often focus on, okay, we're going to electrify end use, and yes, we'll have more electric cars, we'll have all these electric things. The further we get on that, there's this counterintuitive thing that happens. If we electrify less, we actually need more power generation and more supply side resources and the wires that get them places, et cetera, than if we electrify more, because we're going to, instead of taking that electricity and putting it directly into an end use, we're going to be converting it to a fuel, storing it, moving around and applying it that way. Bottom line is we need to build up the entire system. We need to invest more in all 3 buckets of technologies. And we need to build it as quickly as possible. That phrase being defined by how fast you think we need to decarbonize the entire system, whether it's the power sector or the entire economy. So that's the very high level stuff. And so what that means is that, when we look at the transition, let's just talk about the target 2035 that's put out there by the current administration. So you say 2035, what does that mean to me as an engineer and as a modeler and as someone who looks at this from academia? That means we don't turn off zero carbon stuff we have. That means we figure out how to retrofit, replace, refurbish, do things to extend lifetimes and also reduce and eliminate carbon emissions from things we have. So that includes natural gas with CCUS. Where does that make sense? Where does it make sense to retrofit hydro? Where does it make sense to actually do improvements in our nuclear facilities? But it means building out a ton of other infrastructure very, very quickly. And in many of those cases, it's not a technology challenge we're facing. It's all the other soft things that have to happen, the permitting. How do we get something permitted to actually build out infrastructure? I think Maria spoke about it in her comments about how looking at, okay, the optimized solution would be building this new thing over here. I can't get that built. So the practical solution is saying, where do I have low-hanging fruit to say I've got infrastructure at a place? what can I put there that is zero carbon, either by retrofitting that or replacing that? These are questions for us to be asking ourselves.
That's very helpful. And Melissa, just building on that a little bit, the only way we can decarbonize the grid is really to get to the point where we're replacing all of the carbon generating sources, as you alluded to. And do you have a sense, you listed a number of those sources, carbon capture, energy storage, renewables, and nuclear. What the energy mix looks like, assuming first that we can only use the existing sources we have, and then second, what do you see as some of the most promising resources in development now?
Yeah, so when it comes to wind and solar, we're all familiar with those, ramps of cost declines. They look really good. We definitely want more of that in the system if we want to have a low cost system. But at the same time, when I look at, whether it's the Berkeley 2035 study, or it's this work coming out of Georgia Tech from a professor named Emily Grubert, what it shows us is that we have current technologies that can get us maybe 80 or 90% of the way. Let's go with 90. That number varies hugely between regions. So that's a countrywide number. And so what are we going to actually be able to do with the last 10%? Some of the most exciting conversations I am involved in are this mid-step about long-term storage, and actually is zero carbon hydrogen. I'm not going to use a color because there's lots of debates over what color is what and where, depending on what we use to produce it. But we're actually at a place where I don't think we're in a hype cycle with hydrogen and power produced fuels, electric fuels. I think we're in a place where the cost numbers are exciting and interesting and make a lot of sense from a whole systems perspective when we look at lowering the cost of the entire power system. So for me, the most exciting pieces are in that mid-step fuel. And the question is, okay, what existing technologies when it comes to nuclear power, when it comes to any of these power production technologies, including new wind and solar technologies, offshore wind, et cetera, can they play a role in that? How do they play a role? And then back to the infrastructure thing, can we build the infrastructure we need to move those fuels around to the places we need them in? So that's what gets me most excited. It's actually that storage piece in the middle.
Thank you, and really interesting, and it's always interesting to hear, given the hype that hydrogen is starting to get or has been getting, people's perspectives on whether it's real and how real it should be. Moving slightly to your point about the different roles existing and new technologies can play, Paul, let's turn to you for a second, and both for Paul and Chris, what role do you see existing nuclear technologies playing in support of the new nuclear technologies that are under development?
So if I can start from our perspective, a key tenet to our climate planning and our transition to net zero, we've made a commitment now between now and 2030, we'll be 80% reduction relative to 2000 our CO2 emissions, and we'll get to net zero by 2050. That here to 2030 and beyond, one of the base pillars of that strategy is retaining our Cook nuclear plant and making sure that continues with excellent operation for as long as we can get safe, reliable, excellent operation out of it. I think Melissa's spot on. Rule number one is when you find yourself in a hole, stop digging. And so retiring assets that generate power without emitting CO2, that doesn't make any sense at all if you're trying to get to a zero carbon power grid. So Cook Nuclear is incredibly important to our strategy, and we'll continue to retire coal assets and replace them with renewable assets. We've retired about 13.5 gigawatts in the last 10 years of coal. We're going to retire another 5.6 gigawatts of coal between now and 2030, and then we'll add on about 10 gigawatts of renewables between now and 2030, and then continue that progression. But to Melissa's point, how do you get that last 10, maybe 15% of CO2 reduction? And I think that's where R&D is key. It's absolutely essential that we continue to push very hard on that. We're part of the Low Carbon Research Initiative that's being sponsored by EPRI. I think that last 10 to 15% of CO2 reduction, and to your point, Melissa, it depends on where you are, whether it's 10% or 15%. That last bit is still TBD, how we're going to do that. And we're going to need that new technology. And is it hydrogen? I don't know. I think whatever it is, it's some sort of dispatchable power that's going to be able to wrap itself around renewables, not only on a seasonal basis, but almost on an hourly basis.
Chris or Melissa,
anything? Point here. I was going to just add to Paul's point. Something that's very interesting in terms of wrapping itself around renewables is this just isn't about a gap in the afternoons for a few hours. This is about during periods where 2 weeks the wind is weak, you actually need to fill that all of those megawatts, all those gigawatts need to be filled. And so maybe that facility is only operating for a few weeks at a time or even a few days at a time. But when you need it, it's got to have a lot of power behind it. And this is something that is a fascinating markets design question. How do we make sure those facilities are economic, again, to overall have a lower cost of power being supplied to people? And so some of this, again, is non-technical. These are markets questions that we need to sort out, or else we're not going to have the proper incentives there to actually build out what we need, and the solution will be more expensive.
Yeah, to your point, Melissa, I think ERCOT is a great case study that has all the dynamics you just talked about in terms of market issues, in terms of system design issues, in terms of needing long duration makeup power for renewables not available. I mean, there's a lot to be learned there.
Chris, let's turn a little bit more to the new technologies that are being developed. Is there one obstacle to deploying advanced nuclear that you worry about the most or keeps you up at night, and what needs to be done to overcome that?
Sure. I sorry, I just have to add to, even though I'm the advanced reactor developer, I have to, add to Paul's point that the continued operation of our 90+ gigawatt scale nuclear plants is so important for the grid. During multi-day weather events, that's proven over and over, in Florida, and polar vortex in Illinois. It's so important. The other reason the operating plants are so important to us is, we're standing on the shoulders of giants here in the U.S. nuclear industry. Without all of the great safety experience and world-class regulator in the NRC, that existing nuclear industry brings us so much credibility to the world market. Moving on to new technology, as we pursue technologies like Natrium, generation 4 reactors, and we go and take that to the world market. You know what the first question people ask is going to be is, has the NRC licensed this? When we go for a risk-informed emergency planning zone determination, instead of going with the 10-mile deterministic approach. I've already heard these questions. I've heard them in Europe and I've heard them in China. What does the NRC say? So, so much of our credibility as we move forward with advanced reactors is based on that, that great safety experience in the US and having a regulator like NRC. Now, so those are the good things. The worries, I could list quite a few things. Our inexperience on new builds, the need for high assay, low enriched uranium supply. Those are things that I think we're going to solve. If I could highlight the one biggest worry, the one thing we need to work on as an industry, it's some of the things that Maria alluded to. As we go from thinking about maintaining operating plants to siting new plants with a new technology, I think we as a nuclear energy community are going to have to get much better at communication. Our waste story, Maria already pointed to this. When we're talking about operating plants, we can say, yes, it's safe with interim storage. It's safe with on-site storage. The government is responsible for providing a solution. When you're talking about building a whole new fleet like we are, you need a more complete story than that. So we really need to work with policymakers as a country and finish our plan on waste. And Terrapower believes geologic repository is the best way to go. But that's a discussion we have to have with the U.S. government. Closely related to waste, one of the big existential worries for nuclear energy is emergency planning, frankly. I went through high school and college living in New Hampshire, watching Governor Dukakis block the opening of Seabrook over the 10-mile EPZ. Now, as Chairman Hansen has said, if we move to a risk-informed regulatory mode where it's no longer a 10-mile EPZ, it's a risk-informed EPZ that's based on kind of scientific reasons. It's not you go tell the public it's 10 miles and they can understand that. Now you need to be kind of like my boss, Bill Gates, and you need to be a science teacher and explain why, less than 10 miles is okay, because it's a low pressure system, because your coolant, which is sodium, retains iodine. Remember, a lot of people used to hand out iodine pills around nuclear plants. Well, you don't need to do that when you have a coolant that naturally retains iodine and cesium. So, we can all understand that as engineers, but we're going to have to get a lot better talking to the public. And again, I think waste and emergency planning are two huge issues we have to work on if we're going to really build the public consensus that nuclear energy has a place. The technology is going to be fine. We've been working on this for a long time. It's helping the public understand these things.
Thanks, Chris. Paul, yesterday AEP issued its climate impact analysis, which provided insights into what it will take to reach your goal of 100% carbon free by 2050. And how does your Cook nuclear power plant figure into your plans? And were there any other insights from the analysis that you'd like to share?
Sure. I kind of spoke this a little bit before, that the Cook is absolutely essential. Its continued excellent operation is absolutely essential and foundation to us getting to net zero. If you just retire out the coal and add the renewables, we can get down to greater than 80% reduction. But then that last bit, like I was talking about earlier, that's really going to be about R&D and making sure we identify what that combination is. And I think the technology is there, but it's all those other soft things that Melissa alluded to before that are really going to define what's the lowest cost system aggregate when you put it together. And that takes some time. I think we've had some examples of, if you look at the Energiewende program in Germany, where they basically just double their capacity in renewables. There are more cost-effective ways to go about it, and it's going to take the time to lay out that technology piece. I think Chris is absolutely right. The thing I would layer on top of that around new nuclear is that constructability and predictability of construction. That's something that's a really big challenge for us. Not only do we need to be able to demonstrate to the regulator that it's cost effective, that it makes sense, and really demonstrate to ourselves that we're making the right decision for our customers, but we need to have a certain amount of assurance that that's really going to happen. When you talk about nuclear facilities, they're high dollar capital issues that can make or break a company, and certainly be a huge issue for customers for decades. So we're going to need to make sure we get that modular construction, and I think there's a role there for government to play, to take that strategic view as the strategic national view about the reality of maintaining nuclear expertise requires you build nuclear plants, because it's very hard to be relevant on an international stage if you're not doing anything new. And so I think there's a real role for the government to play there, and we're going to have to demonstrate some amount of reliability and predictability around delivering these projects.
Thanks, Paul. We have a number of questions from the audience. One from Sven Bader, who said load following is often cited as a primary need for future energy sources that are not wind or solar. And this is for the whole group. How quickly will these load follow energy resources need to respond to, for example, calming of the winds in a wind intensive grid? And is this an hourly plus or minus 10% power needed? And is nuclear capable of such quick response?
Wow, those are really great questions. I guess if I could just offer part of an answer, I think some of that is to be determined. I don't think we need to look to one technology to do that, right? If you're looking to respond on a 1 to 2 or 3 hour basis, then you may just use existing energy storage devices. If you're looking for longer term dispatchable power, the type that Melissa alluded to, then having those dispatchable resources that are there, and that's why the Natrium technology, having the energy storage integrated into the system, where you can advance that for hours at a time to handle the duck curve, for example, for solar power. So I think it's going to take a combination of technologies to really put it together. That's why it's planning the system as a whole integrated entity is very important, and then that gets to the market design kinds of issues around how you're able to do that.
And this brings us back to a point in your first question, Josh, which is about like, what does the grid need? The grid needs a lot better communication. We're still figuring out how to manage these two-way flows of information and power. I mean, we've been working on it for a while. We know a lot more than we did 10 years ago, but we're still working on improving that. So it's interesting because we talk about the different types of problems broadly that we're trying to solve. It's interesting when we talk about a resource, a supply resource, fading down unexpectedly for a matter of hours, well, that's something that can be addressed through short-term storage, sure, but also, demand response, demand reduction. And, hopefully we don't end up, I'm in Texas and lived through the freeze last month, didn't have power for 4 days. I mean, hopefully we're not trying to fill 4 days worth of gap, on a routine basis. If so, we got to redesign our risk calculations if that's where we end up. The point is, when you think about different tools and different things, I think about a power plant as, okay, this is a host of things it can do for me. It can provide lots of different services. So how do I make sure that it's allowed to provide those services and get paid for them in the system? Let's make sure it can do all those things. And then not pigeonholing one resource into one application, unless, when you do the analysis and you look at the whole optimization, it's clear that that is actually the best role for that technology. And, in which case you need to create a structure for it. So nuclear, other baseload, other flexible things that are just dispatchable. So they're there when we want them to be. Sometimes we will want them to play that kind of complementing wind and solar. As Paul just said, we're looking a few hours ahead to kind of buffer duct curves. We can also look at demand response for pieces of this, but it's about not getting so focused on actually one technology. And Maria brought this up, but actually creating a system where all the technologies can play. They can all be paid for the things we actually care about, which is the lights being on, the beer being cold, whatever analogy you want to take today, but have all of those. That's what we want to make sure of. Once we do that, a lot of these things work out.
Yeah, so I was about to start talking about load following, and I think it's so good Melissa started with this importance of interconnection, because it's an area where we're weak in the U.S. I remember meeting with Jean-Bernard Lévy, the chairman of EDF last year, and he was explaining they have great interconnectivity in Europe, and in his words, when the sun comes out in Spain, they can spill hydro in Switzerland. They're really that connected, and we aren't in the U.S. And you can see that in with things like ERCOT. You can see that with state isolated IRP processes that are kind of pretty static processes that have worked for the last 30 years when demand growth has been a few percent, but now we're looking at the next 30 years where there's just these huge dynamics with electrification of transportation, shutdown in coal, all this intermittent wind and solar coming on. So the next 30 years is going to be so much more dynamic. We need to be more interconnected. But so interconnection first, then then load following. So many times utilities have come to nuclear developers saying, "Can you load follow?" And typical problems are it's fatigue on your component design. It's a transient on your fuel that's sometimes hard to deal with. I've even had operators tell me, when they've the large Gen 2 plants have been asked to load follow, maybe because they have hydro in their network and they want to use the hydro. They have to put extra control room operators in there to to have extra eyes and ears on the panel. So, nuclear hasn't, whether it's operational concerns or engineering concerns, load following has been, kind of a challenge. So again, what we did with Natrium is the reactor doesn't load follow. The reactor operates at 100% rated power all the time, which is good because for another reason, because the nuclear asset is the most expensive. Even if it's a cheaper reactor, it is the most expensive asset on the site. So the idea with Natrium is keep the reactor going at 100%, store the extra energy when wind and solar are up, store that in molten salt, and then ramp up and down with your energy island, much like a concentrated solar plant does when clouds are going by and other transients are happening.
Thanks, Chris. Melissa, I want to get back to your last point, and Chris alluded to this in his comment as well. We've spoken a lot about electricity, but one of the benefits of nuclear is the capability to operate at high temperature and help decarbonize industrial or transportation energy uses as well. And What opportunities do you see for advanced nuclear in this space?
I mean, this is a great point, Josh. Just around, we like, it's a great clickbaity title, Electrify Everything. Actually, the real title is Electrify Everything That Makes Sense to Electrify. See, this is why I'm not a journalist, right? Electrify everything that makes sense to electrify, and realize that in some cases, we're talking about high temperature heat applications, particularly in industry, where you need really hot stuff to create what we want. So you can electrify some parts of the process, but it doesn't make sense in others. And so, when I look at nuclear, again, it's like I'm not seeing the technology, I'm seeing the outputs, and I see electricity, and as you say, hot, like really hot, high quality heat that I can use for different applications. So the biggest bang for the buck that I see, I mean, people can talk about district heating networks and actually putting heat into those types of systems, maybe not as much in the US, but in other countries. But I actually see it as being direct industrial applications. And then we have questions about, where are different competitive advantages of building up different parts of you. So, I mean, that's where I see the biggest opportunities. And I would point.
And Melissa, we may have some connectivity issues. This is quintessential 2021, unfortunately. Melissa, we've lost your audio. So we'll give you a minute to come back to that. Let's hopefully the internet was restored. For Chris or Paul, just wanted to see, building on the comments Melissa was making about the benefits of nuclear beyond just the electricity generation. And Paul, for you, as you think about the future in your industry, do you envision your company potentially going beyond electricity production and getting into things like supplying low carbon fuels, industrial heat, or other energy products, as Melissa was just discussing?
Well, I think we're an electric company for now, and that's going to be our focus, and transitioning our fleet to where our customers need it to be by 2050. That'll be the focus. But certainly there are other opportunities, and that may not be something that we centrally focus on. It may be something we partner with others on. But really, kind of powering people's futures is what we're about, and trying to provide that power that people need to live their lives. So I think there are opportunities and potentials where it could go elsewhere, but certainly nothing in the mill right today, at least that I'm aware
of. Melissa, now that we've resolved the internet side, turn back to you for a moment.
Spectrum knew I was getting very loving this discussion about industry. I'm not sure much y'all had heard, but effectively, nuclear has this advantage of being able to produce high quality heat and electricity. So the question is, how do we want to actually use these things? So I was directing people to some work by my colleague Julio Friedman and a gentleman named Chris Bataille, who's part of the IDRI project, so the Deep Decarbonization Pathways Project. He's a Canadian working in Canada and a number of other countries. And he says, you know what, I'm going to take on the hardest of the hardest to abate sectors and see what the different applications are. And it comes back to heat so often. So these are great questions.
And so we share Melissa's vision there that nuclear heat brought to industrial processes can be just a great way to fight climate change, right? Most of the CO2 doesn't come from generating electricity; it comes from industry, transportation, etc. So whenever we can bring the heat directly to the need, that's going to be the most efficient and economic. Because one thing to remember is, as soon as you electrify, as soon as you use the nuclear energy to make electricity, you may have an advanced reactor, but it's connected to a 100-plus-year-old Rankine cycle that steals 2/3 of your energy and sends it out the cooling tower, right? So if you can deliver the nuclear heat directly to an industrial load and not lose that energy to the Rankine cycle, you just triple improved your economics. So that's definitely our vision. But if you think about licensing these first few advanced reactors, we're probably going to do that with a pure electricity play. Electricity demand is growing. We happen to have a reactor that works well with wind and solar. So our first reactors are going to be, pure electricity plays, implementing that storage that I described to you. But when we think about 2050, we think about nuclear power plants like Natrium or like our molten chloride fast reactor. We think about them providing heat, to make electricity, but also to directly feed high temperature processes. And one thing to remember also is many of these advanced reactors like ours operate at higher temperatures. So light water reactors are 300 centigrade. Natrium, the sodium plant, is 500. Molten salt 700. High temperature gas even higher. And when you go higher, you can drive different processes that you can't drive with a light water reactor today.
So, Chris, this is a perfect segue to the next question from David Dixon. We assume that the significant test data on the new fuel types will be needed to support new reactors, and that may require the newly authorized test reactor at INL. And what's your sense of the schedule for that new reactor, and when will test data be available, and how important is it to have the new test reactor before bringing new reactor types online?
Yeah, so gosh, I spent a lot of time with Clay Sell at X Energy for the two demo projects. Ours and X Energy's. We don't rely on BTR testing to deploy our demonstration unit. In our case, we're using a metal fuel for our natrium sodium fast reactor, and it's a metal fuel that was developed based on the legacy U.S. Sodium reactor program, on top of some international benchmarks, and then frankly some materials testing that Terrapower has paid tens of millions of dollars for, where we went to Russia to Bor 60 and tested our materials. So we have what we need for natrium, and that's why I think these demonstration projects need to be at the very top of the DOE priority for funding. But if you go look at Russia and China, you'll see they have the equivalent of BTR, and the reason we need BTR in the long term is we're going to have many advanced reactor developers in molten sodium, molten salt, gas. BTR is going to be able to test materials and components in the fast spectrum for all those plants. And just think about the fuel improvements that have happened on LWRs over 50 years. It's night and day, the fuel we have today versus what we had 50 years ago. Imagine the kind of improvements we could make on advanced reactors. And if we had multiple, U.S. origin advanced reactor projects, and on the side we have a government user facility that lets folks, without bothering the commercial customers, lets folks do component and materials development. I really think that would enhance the this new wave of advanced reactor development. But by far the biggest priority needs to be on the advanced reactor demo program. If we don't go off and demonstrate a couple reactors in this country, everything we've been doing the last 20 years in the labs and at companies like Terrapower is kind of still in a lockbox. We really need to demonstrate.
Well, this is a helpful segue to the next question. And the Union of Concerned Scientists recently published a report that was entitled "Advanced Isn't Always Better." And in this report, they recommended the delay of all action to develop new reactors and focus on the safety and cost effectiveness of current reactors. And for any and all of the panelists, have you read the report, and could you comment on those recommendations?
I can, but I just finished. I'll let my colleagues go first, and I can supplement.
Melissa or Paul?
So I haven't read through the whole report, so I was going to pass it to Paul or Chris if they've read the specific report. I have thoughts on the broad concept, but I think that's best as the third set of comments on this.
I have not read the report as well.
So Chris, we'll turn to you, and then we'll throw it over to Melissa.
So so I've spent my whole career working on nuclear energy. First in the Navy, and then on civilian light water reactors. 6 years ago, I joined Terrapower, but I've been a light water reactor operator, manufacturer, designer. I refueled them. They're so very safe. They have a great record. And when I came to Terrapower, I kept that conviction that today's light water reactors are very safe. They should be extended not 40 to 60 years, but 60 to 80. But the more I learned about reactors like Natrium, a sodium-cooled fast reactor, I really gained an appreciation for the added inherent safety features. The fact that a sodium-cooled reactor operates at atmospheric pressure is just a game changer. I don't know about Paul, but I feel like I spent most of my career in pressurized water reactors, worried about proximity to boiling. Operators are thinking about it all the time. It drives the need for ASME Section 3 pressure vessels and really serious welding quality requirements. It drives you to have to go to Japan Steel Works to get your forgings because the facility doesn't exist in the US. So low pressure is a game changer for safety and even for manufacturability and cost. The other thing is this, several hundred-degree margin to boiling. When you're operating a sodium fast reactor, you're hundreds of degrees from the boiling point of the coolant, sodium. Again, another game changer. Sodium, liquid sodium it just naturally retains iodine and cesium. A game changer. So you can show all of these things in your safety analysis, in your source term calculations, and you can even take it to your emergency planning zone calculation. We don't share the same view as the report. I have personally spent many hours operating light water reactors. They're very safe, but I can see the safety benefits of advanced reactors like Natrium and how they take you to that next order of magnitude lower accident frequency.
So innovation shouldn't stop as there's a continued evolution with the existing technology. Melissa, turn to you on this, and then we have time for one last question.
Well, I find that in discussions, and I work for an academic organization, I have no skin in the game, and we don't advocate. And I'm not saying this technology is the best, this technology is the best. It's like, look, all the technologies have potential roles they can play. And if the problem I'm trying to solve is decarbonizing a power sector, I want a lot of options. And I think when I speak to grid operators, they want options. They want different levers they can pull in different situations. And so we end up in these conversations that often digress into a couple of different things. One is technology tribalism around like, I'm for this and I'm against everything else. Well, that's not productive. It doesn't get us to the solution. But then on the other side of things, you touched on it earlier, Chris, like about education and communication. It's understanding where the concerns are, having a conversation about it, and really digging into, okay, what are the problems we're trying to solve? What are the suite of things that can work at a high level? And then what's going to actually work in a particular community? What are their priorities? What are their restrictions? Do they have water restrictions? In which case, some technologies are out the door. Do they have very flat land? Do they have hilly land? I mean, there's lots of different things that factor into this, good and bad wind. So, I cannot speak to the specific report because I haven't gone into it, but this overall conversation, where I come at it as a modeler is, what is the problem I'm trying to solve, and what are the things that I could potentially use in that? Realizing that reality is never going to be my cost optimized pathway. It's going to have so many other factors that are not contained within, I'm an engineer, my techno-economic kind of suite of things. So those are the comments I'd make. I just having that broad conversation, understanding where concerns come from, addressing them, and realizing we're going to need a lot of tools to get where we want to go if where we want to get is zero carbon.
Yeah, if I could just add one comment. I mean, if you look at light water reactors in general, and particularly light water reactor designs, existing reactor designs within the United States, I would say that the safety record is extremely strong and extremely deep. So I think it's a demonstrated technology. I think it's demonstrated as a safe technology. But to Chris's point, there are amazing opportunities to increase and improve safety, and to reduce costs, and to reduce flexibility through advanced reactor dyes like Natrium. And I think we'd be foolish to turn our backs on that.
Well, that's
Josh,
fantastic.
I'll just say the last point. Oh, I know we're running out of time, but We need to deploy and we need to innovate. That's something the research shows very clearly. We need to walk and chew gum. I don't know the right analogy, but we need to do both things if we really want to get to a whole solution. That's also very clear in the research. But Josh.
And that is the perfect place to end this conversation. There is urgency to act, to innovate and deploy all at the same time, and operating otherwise is perhaps a false choice. This has really been a fantastic conversation, and thank you to Paul, Chris, and Melissa for taking time to have the conversation we've had, and thank you to NEI for hosting this informative event today. And finally, thanks to all of you in the audience for tuning in and for the fantastic questions we've had. It's really been a pleasure.